I am Naomi, and I will be teaching this full form. And today we will be going over some basic chemistry to help us out with the rest of the school year. Okay? The first topic, as you can see on the screen, is the states of matter. This is very important for everyone to know and to be comfortable with. It is nothing to be afraid of. It is very easy to understand, and if you are struggling, feel free to use my office hours to come and ask a question. Okay? Alright, the states of matter. So here we have some figures to or shapes to represent the three states of matter that we're going to be talking about. Okay? So right here is the solid, and over here we have the liquid, and lastly we have the gas. All right, now to make this make a little bit more sense to you, in the case of water, we all know what water is, right? So in a solid form, we would say that water would be ice when it's a solid, right? We know what ice is. We put it in our drinks to make it cold. And usually water becomes ice when the temperature falls below 0 degrees Celsius, okay? That would be the melting point. When it's in the liquid form, we simply call it water, right? And that falls between the 0 degrees Celsius and 100 degrees Celsius. And in the gaseous state, we would call water, or H2O, we would say that the H2O is steam. And usually that is at the boiling point and above when the liquid turns to a gas. It becomes steam, alright? Let's look at the particle theory of matter. A lot of words. Simple. Particle theory of matter. What is matter? Matter is anything that has mass and takes up space. Do we understand? It's that simple. It's anything that has mass and anything that takes up space. Okay, based on that little definition, can you tell me which of these is matter? So here we have a person, we have an apple, we have a donut, and we have a football. Which of the following is matter? So I'll give you 5 seconds to tell me. You can write it down, you can take it, or just hold it in your brain. I'm going to show you the answers in 1 second, okay? Alright, so yes, made up of matter. If you thought that the apple was matter, you're also correct. And yes, the donut is matter and the football is matter. It's all matter. Why? Because these all have mass and they all take up space. Good. Now what's the purpose of this theory? This simply helps us to understand the behavior of matter. Okay? And here are some key points. All matter is made up of particles. And what are particles? We have atoms, molecules, and ions. Right? Yes, if these words are strange to you, don't worry, I have you covered. So an atom is the basic unit of matter which cannot be broken down by chemical means. Okay? A molecule is a particle consisting of 2 or more atoms. And an ion is simply a positively or negatively charged atom. Another key point is that particles are always in motion, and there's a theory specifically focusing on that, but we will get there in 1 second. Forces of attraction and repulsion exist between particles. There are spaces between particles, and the temperature of particles are affected by how quickly they move. Okay, is it making sense yet? No? Okay, let's move forward and see if it makes a little bit more sense. Now, we have this guide to describe. And when someone asks you, okay, can you tell me about the particles in this solid? Okay, can you tell me about the particles in the liquid? This is how we're going to tell them. So first we're going to look at the arrangement of the particles. Then we're going to identify their proximity, which means we're going to be focusing on how close they are to each other. Next, we're going to look at the motion of the particles. We're going to speak about this. And then we're going to focus on the force of attraction. Okay? So as you can see here, we have the arrangement, proximity, motion, and force of attraction, right? And here's our solid coming bouncing in. And if you look at the arrangement of these particles, each of these circles, each of these spheres are the particles. These represent the particles. So as you can see, we have a regular pattern. They're in columns coming down and they are in rows. They're so neat, you know? That's what we would call a regular pattern. And then we would discuss the proximity. If you look here, you will see that these particles are touching. They're very, very close together. And the motion of these particles, we can't see that here, but you need to know that the particles vibrate about a fixed point. Okay? And lastly, we are supposed to focus in on the force of attraction. And the force of attraction between these particles, you would say that they are very strong. They're held together because of the force of attraction between them, which is so strong. So this is extra information that I placed down here to say that solids do have a definite shape and volume. They can't be compressed and they do not flow. Why? Due to the strong forces of attraction. Now let's look at the liquid, and here comes the liquid. And if you look at the arrangement of the liquid, you will see that they have an irregular pattern. You can't really pick out any rows. Maybe right here you would see a row, but it's not straight. See, they're all jumbled together. There's no real structure to it. You understand? So you would say that the arrangement of these particles are irregular. They form an irregular pattern. The proximity, they're touching. They're very close together, just like the solid. But the motion, unlike the solid, of the particles, they slide over and around each other. And the forces of attraction of them are weaker than in solids but stronger than in gases. They just make up the in-between. Liquids have a definite volume but not a definite shape. Make sense? They can flow. They take up the shape of their vessel and they cannot be compressed easily. Why? Due to their close proximity to each other. Now let's look at gases. Now we have this to represent our gases. As I told you, the spheres are the particles. So we don't have many particles here, but these particles will be used to represent the gas particles. And as you can see, they aren't regularly arranged. There's no focus. They aren't in line. There's no sequence. They're just there, wherever they feel to be, The proximity, you can clearly see that these particles are far apart. When you look at the solid and the liquids, you will see that the particles are touching. They like to be around each other. With the gases, they don't seem to be friendly, They just move away from everyone else. So they're far apart. And the motion, they move randomly. They move randomly and they move rapidly. The force of attraction, almost non-existent. That's why they're so far apart. Gases have neither a definite volume nor shape. They have a low density, can easily be compressed, and they move everywhere. Why? Due to their far distance apart. Kinetic theory. Remember I said that we're going to be looking at the motion. There's a theory specific to the motion. This is what I was talking about. The kinetic theory. Particles in matter are in constant motion. This is basically the idea of kinetic theory. Kinetic meaning motion. They're moving. There's energy behind this motion. Alright. Diffusion. So the kinetic energy, the theory is supposed to be powering this concept of diffusion, right? And why I have this in red is so that you use this definition. The spreading movement of a substance through another due to the random motion of the particles. And of course, this definition isn't wrong by saying the movement of particles from a region of high concentration to a region of low concentration. That is not wrong, but this is a better definition. And lastly, please note that gases diffuse much faster than liquid. Now let's look at this little experiment I put together for you guys. We have a cotton, this is a tube, attached tube, and we have them, these are rubber bands, so they're sealing the tube. This is supposed to be a cotton wool, and this is also a cotton wool. So this cotton wool over here is soaked in ammonia, and this one is soaked in hydrochloric acid, and the hydrochloric acid gives off hydrogen chloride gas. Now the idea of this is that because gas particles are in constant motion, all particles in matter are in constant motion, but gas particles will move rapidly and they will bounce around and just try to move along the tube, right? And this is called diffusion because they're not in high concentrations on the other side of the tube, so that's where they're headed. Okay, so one of these particles have particles that are lighter than the other. So for example, if they are the same weight, they will probably meet somewhere around here. If this is lighter, maybe they will meet around here because this is too slow to get to the other side as fast as ammonia reaching over here. So let's see what happens. So a few minutes later of setting up this experiment, you will see a white solid forming right here, which means that the ammonia diffused faster than the hydrogen chloride gas. And this solid that has formed is a reaction between the hydrogen chloride gas and the ammonia, forming ammonium chloride. So this is proof that particles did move from here and they'd also moved from here. Okay, let's look at the other diffusion experiment in the liquid. So I'm going to put, this is water, and I'm putting potassium manganate 7 or potassium permanganate into this water. That is what is supposed to be happening here. And what simply would happen is that it would, in quote, dissolve. We like to use the term dissolve in our everyday life. So this would dissolve, meaning that it spreads evenly throughout the water. You see that? Now, in an actual lab, if you carry out this experiment, the water will turn from its clear solution to a purple solution because the potassium manganate is purple. And this is another example showing you how diffusion works, okay? Osmosis. What is osmosis? Now, this is a specific form of diffusion catered to water. Now, we would say that osmosis is the movement of water molecules through a selectively permeable membrane from a region where the water is in high concentration to one of lower water concentration. Let me let that sink in. Give you 3 seconds to let that sink in. It's the same concept of diffusion, except there's a selectively permeable membrane and we're talking about water molecules. Next, another topic that is important. So let's look at the changes of state. Now, we already discussed the states of matter, and the states of matter would be the gas, the solid, and the liquid. Alright, and now we're going to look at the changes that occurs between them. So a liquid to a gas, gas to solid, and so on. So when we are seeing a liquid turning into a gas, we would call that boiling or evaporation. Boiling occurs at boiling point. Evaporation is the escape of the molecules off the surface of a liquid. Okay, gas to a liquid is called condensation. You know when you cover down your pot of boiling water, and you see that water molecules, you see the steam coming up, and then when you cover it down, all of a sudden you see the water molecules forming on the cover. That is what you call condensation. Freezing, we spoke about this already. Liquid, that's for example, water to ice, that's freezing. Um, Ice to water, solid to liquid, that is melting. Gas to solid and vice versa is what we would call sublimation. Okay, the periodic table. The periodic table is this huge, scary table with all the elements in chemistry, but don't be nervous. Trust me. Now let's look at the history. It's important that you know the history. Dober-Reiner's triads, 1817. Here's a cool picture of him from Wikipedia. Elements can be grouped together in groups of 3. This is his idea. This is not what we are using as our periodic table today. But here is the history of it, and this is how we reached this point of understanding the periodic table that we do have today. Okay, so the elements can be arranged together in groups of 3 according to their physical and chemical properties. Okay, the triads were linked with an increase of atomic weights, and that atomic weights is what we would call today atomic mass. Okay, the middle elements of most of the triads had an average weight of the first triad and the first element of the triad and the third element of the triad. I am so sorry, guys. Some of the triads had the same chemical properties and others did not. So now we can see some fault in this periodic table. Okay, now if you look at this is what we would call a triad. This is another triad and this is another triad. Okay, the atomic mass of this one and this element, this should be the average of 2 of these. So when you add 7 and 39, the atomic mass of 7 of lithium, which is 7, and potassium, which is 39, you should get an average of 23, and that is why we have sodium in the middle of that triad. So that is the idea of these triads. Okay, and a lot of the time, as you can see, it wasn't as exact, but it was close enough. Next, we have Newland's laws of octaves, 1863 and 1866. Now, the elements were listed according to their atomic weights. As I said, the atomic weights back then is what we call the atomic mass now. Elements which are similar were separated by intervals of 8. So every 8th element had a similar property. Okay? So in basic terms, for example, every 8th pencil would have been black. Every 8th, and then the other 8th pencil would have been green, and so on. But that is not the exact case, but that's supposed to be an example. I hope that is helpful. Let's look at Mendeleev's periodic table, 1869. Now this one brings us so much closer to where we are today. But it took his second attempt at this periodic table to develop. It was the second attempt that helped us form the modern periodic table. Okay? Not the first one, the second one. So his reasoning was based on the chemical characteristics. Elements were listed according to their atomic weights. The elements were arranged in groups and periods. And as you look at our periodic table today, they also have groups and periods. Okay? The groups are the columns, the vertical columns, and the periods are the horizontal rows. Many elements were not yet discovered, and this left gaps in the periodic table. So it looked a little, what we would say, scanty. You know, there was something missing. And the tables showed a gradual change in the properties of the elements of this periodic table. Now, his first name was Demetrius. So if you're wondering why do I have Demetrius' first periodic table and I just told you about a man named Mendeleev, please, this is part of his name. So this is what it would have looked like, his periodic table. You see? Okay. Now this is the periodic table we are accustomed to. This is the modern periodic table. Now, remember I spoke about the groups and the periods. So we have group 1, group 2, group 3, 4, 5, 6, and 7, and then we have group 0. And I will explain the characteristic of group 0 when we are speaking a little bit more of the groups themselves. Okay. We could see that the elements are numbered like I just showed you. The group 0 elements over here are called noble gases. And these were discovered after Mendeleev's periodic table. They came after. So these were the brand new elements, the ones that were missing. But so on, as you can see over here, all of these are metals except hydrogen. We know that hydrogen is not a metal. But everything else though, metals and transition metals, over here we have metalloids. There's this staircase. I'm sorry I didn't have it outlined, but there's a staircase pattern separating the metalloids from the non-metals. So all over here we have non-metals. The first 3 periods here, we would call these the short periods. As you can see, they look like they're just missing something. It's just hydrogen and then helium, and then there's this huge gap between here, but the rest of the periodic table has no gaps as such. So that is why we would call them short periods. As I said, the periods go across. These are the rows. All right. So across each period, you can see a gradual change in properties from metallic to non-metallic elements. Periods 2 and 3 is a similar change in physical properties such as the boiling points. Okay, good. And why do we have metalloids? I know I used the word and I didn't explain what metalloids were, but metalloids simply have some properties of metals and they also have some properties of non-metals. Alright? So let's look at the features of the periodic table. The elements of the periodic table are arranged in order of atomic number. So let's go back. So you see, there's this little number right here, right there, and we call that the atomic number. And the atomic number is the number of protons that are found in the nucleus of the atom. Now, we would go further into the atomic structure. We'll actually go through that topic next time. But for now, we would say this is the atomic number. And you see it increases by atomic number 1, 2, and then we go 3. And this is the next row, and then we go from 11 and go on. So it goes this way. The numbers increase horizontally. Alright? Elements in the same group have the same number of valence shells. Valence shells are simply the outer shells. As I said, this will all make sense when we go through atomic structure. But for now, let's just say they're the outer shells. The atoms have shells, and they increase as you go down the group. Okay? Right. For groups 1 to 4. I lost my train of thought just now. So if you're wondering what just happened, I lost my train of thought. But I'm back. For groups 1 to 4, the number of valence electrons are equal to that of the group number. You're like, what does that mean? Okay, we have these numbers here, 1, 2, 3, 4, 5, 6, 7, and 0. So in this row, right, on the last shell of the atom, you will have 1 electron. On this one, you will have 2 on the valence shell. So when we come to this one, this is supposed to be 4. How many do you think are in the outer shell? 5, 7? No, 4. Why? Because it's in group 4. Group 7 has 7. Look at how easy that is. Basic. Is in group 7, it has 7. And for group 0, all the ones in group 0 usually have 8 electrons in the outer shell. Helium only have 2 electrons, so they have no more than 2 electrons. So this would be the exception. But most of the other ones have 8 in the valence shell. So when you see group 0, just think of it as 8, okay? Group 0, as I said, exactly. As you go across the period, the atoms of elements have their valence electrons on the same shell. Let me make that make sense. As you go across here, say this is the second period. No matter how many electrons are in the valence shells, they are going to have the same amount of shells. So here, 1 shell. This row, 2 shells. This row have 3 shells. It's just that the third shell would have the electrons according to the group they're in. And the period number, as I said, that means is equal to the number of shells. Now, to finish off today's session, we are going to zero in on the trends in group 2, and we're going to go over the trends in group 4 in the next class. So trends in group 2. Group 2 elements react with oxygen, whether the oxygen is in air or in pure form, to form oxides. So here we have a reaction occurring between calcium and oxygen. And what this yields, or what this forms or produces, this is what this arrow means, yields, forms, produces, any of those words can work. And here we would have a calcium oxide. As we said, group 2 elements react with oxygen to form oxides. So if it was magnesium, what do you think we would produce? I'll give you 2 seconds. Exactly. You're correct. I'm sure. You produce magnesium oxide. Good. Most elements in this group react with water to form a metal hydroxide and hydrogen gas. Okay, too many words. Mg, magnesium, and H2O, water, they react with each other to form magnesium hydroxide. This is the metal hydroxide. Magnesium hydroxide and hydrogen gas. And this is given that this reaction occurs when the water is cold. But if this reaction occurs in steam, instead of magnesium hydroxide forming, we would simply have magnesium oxide and hydrogen forming. Okay? So, given that the general idea is that this metal reacting with water will form a metal hydroxide and hydrogen gas. If I use calcium, what do you think would happen? We would have calcium as the solid, we would have water, and what do you think we will form? 2 seconds? You think about it? You got it? Okay. We would form calcium hydroxide and hydrogen. Okay, good. Now that we are on the same page, moving on. Elements in group 2 react with hydrochloric acid to yield metal chlorides and hydrogen. As you can see, I was using to form, and to yield so that you could familiarize yourself with the language. Okay? I could have used produce here. All mean the same thing. So elements in group 2 react with hydrochloric acid, and this is the formula for hydrochloric acid, to yield metal chlorides and hydrogen. Alright, here we have calcium, the solid metal, reacting with hydrochloric acid, and boom, we have calcium chloride. You see, that's the metal chloride. Calcium chloride, metal chlorides. Is it making sense? You have hydrochloric acid, HCl, and you're going to form calcium chloride and hydrogen. Good. Now that is the end of our class today. I will go into detail, as I said, and focus on group 4 elements. And then I will touch base. Actually, I will start to teach atomic structure next class. So please be prepared, do your reading, whatever it takes to make you comfortable. But please be ready for the next class. Thank you for watching. If you're watching on YouTube, thank you for joining the class, and I will see you in the next 4th form chemistry session.